ions and their coordination entities is similar irrespective of the ligand. Is it right? Yes. Do not predict the tetrahedral and the square planar shape of the coordination compounds which are having the coordination number 4. If the ligands are weaker, then splitting is also get weakened and it is also known as weak field ligand. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called coordination compounds. Under that, we have discussed about the Werner theory of coordination compound and we have learned that what is an primary valency and secondary valency and it was given by the Alfred Werner. And also we have learned about the limitations of Werner theory and we also talked about the valence bond theory. Under that we have learned about the applications of valence bond theory by understanding the octahedral complexes as well as with the tetrahedral complexes. Today let us move on to the next topic of this unit by understanding the magnetic properties of coordination compound. And we are going to understand the limitations of valence bond theory also and we are going to deal with new theory called as crystal field theory and we are going to understand the spectrochemical series in that and the electrons in the d orbitals of the metal ion in octahedral complexes, how does it behave, that is also we are going to understand in this session. Let's see what is the magnetic properties of coordination compounds. So we already studied that especially the coordination compounds, it shows the magnetic behavior. Only when the presence of unpaired electrons is there, it will be attracted towards a magnetic field, hence it is known as what? Paramagnetic. If there is no unpaired electrons in the coordination complexes, what will happen? They are not attracted towards a magnetic field, instead of that it repels from the magnetic field so that they are said to be diamagnetic. Is it right? Yes. The magnetic moment of the coordination compounds can be measured by magnetic susceptibility experiment and the results can be used to obtain the information about the structure which has been adopted by the metal complexes. For the metal ions, up to the 3 electrons in the d orbitals like titanium 3+, vanadium 3+, and chromium 3+, has 2 vacant d orbitals which is available for the octahedral hybridization with the 4s and 4p. Here we have examples of vanadium 3+ and titanium 3+ as well as with the chromium 3+. All these are the central metal atoms which are consist of vacant d orbitals. Which consists of what? Vacant d orbital. You can see that in titanium we have 4 vacant d orbital as well as 4s and 4p. Similarly, if it comes to the vanadium, it consists of 3 vacant d orbital as well as with the 4s and 4p. If you consider the last one, that is chromium, it consists of only 2 vacant d orbital for the hybridization and totally from all these example you can see that it consists of 2 empty d orbital for hybridization with the sp, hence their hybridizations are known as d2sp3 hybridization. Okay. So, this indicates that the presence of unpaired electrons in the coordination complex which are responsible for the attraction towards a magnetic field, hence they are paramagnetic as well as it is diamagnetic if it is repelled from one another. So, the magnetic behavior of these free ions and their coordination entities is similar irrespective of the ligand. Is it right? Yes. When more than 3d electrons are present, which is required for 3d orbitals for the octahedral complexes is not directly available as according to the Hund's rule, and thus in the d4, d5 and d6 cases, the vacant pair of d orbital results only by pairing up of 3d electrons which leads into 2, 1 as well as with the 0 unpaired electrons. So first I'll go with the D4, then D5 and D6. We'll see what is D4, D5 and D6 by taking chromium 2 plus and manganese 3 plus as an example. So in these two examples you can see that the 3D orbitals which consists of what? 2 D empty D orbitals, hence, and 1 S and 4 P orbitals will be there. Hence it is known as sp3d2 hybridization. Clear? Similarly, if it is D2 sp3, you can see that there are 2 empty D orbitals will be there and 1s and 3p and give rise to the D2 sp3. This indicates that especially with the manganese, the complexes will be manganese cyanide 6 and 3 minus. Similarly, I can take FeCN6 3 minus. In the first example, that is hexacyanide-manganese 3 ions, in that you can see that it undergo D2 sp3, that is sp3d2 hybridization it undergoes. Hence it is clear from that it consists of what? It consists of 2 and 3 unpaired electrons, hence they are paramagnetic in nature. We'll see with the D5 also. In D5, especially with the central metal atoms like Mn2 plus and Fe3 plus, the 3D consists of 5 unpaired electron, whereas 4s and 4p and 4d are empty. Hence it is sp3 d2 hybridization. If it is d2 sp3, you can see that these electrons will be get paired up, okay, and results in a formation of what? 2 unpaired electrons in the 3D and there is only 1 unpaired and remaining 2 empty D orbitals. Hence it results in a formation of what? D2 sp3. This indicates that even though this complex which is formed by pairing up of electrons, which consists of 1 unpaired of electron, hence they are paramagnetic in nature. We have one more example of D6. Here you can see that in a 3D orbital, it consists of 1, 2, 3, 4, 5 and 6 electrons. When these electrons are started pairing up, all the 6 electrons will be get paired up and results in a formation of D2 sp3. So in this, you can see that there will be no unpaired electrons. Hence, this cobalt as a central metal atoms which are diamagnetic in nature. Which are what? Diamagnetic in nature. The example is C2O4 3 plus. Okay. In this complexes, the cobalt which exists in a +3 oxidation state and it is diamagnetic in nature because there will be no unpaired electron because these electrons will be get paired up and results in the formation of D2 sp3 hybridizations. So hope you all understood with the D4, D5 and the D6 orbitals in the coordination compounds. Now let us see what are the limitations of valence bond theory. So already we have understood that by understanding the valence bond theory, we can predict the shape, we can predict the geometry and we can predict the hybridization. But actually by understanding this valence bond theory, there is a lot of assumptions we have made. Is it right? Yes. And it does not give a quantitative interpretation of the magnetic field. How does the magnetic field will be explained based on the valence bond theory is not clearly explained. Then it do not explain the color which is shown by the coordination complexes and do not predict the tetrahedral and square planar shape of the coordination compounds which are having the coordination number 4. And it does not distinguish between the strong and a weak ligand. So these are the different limitations as we have come across from the valence bond theory. Remember, we can predict the shape as well as we can predict the geometry of the given compound, but we cannot predict their actual structure if the coordination number is 4. and it does not talk about the strong and weak ligand. When I am talking about the structures which is explained by VBT, I have used the term strong and weak ligand. There is no basis for the strong and weak ligand which is not clearly explained by VBT, and also a lot of assumption we have made during the hybridization. So hope you know that assumptions also. So these are the limitations of what? Valence bond theory. Next we'll see the crystal theory or crystal field splitting. The metal-ligand bond is considered to be ionic and which arises purely from the electrostatic interactions between the metal and ligand. First of all, why we need to study this crystal field theory or crystal field splitting? Because as we have come across from the VBT as well as from the different concepts of the coordination compounds, the structure of the atom, the color in the atom and the geometry of the atom and the nature of the strong and the weak ligand was not properly explained. Those concepts which is clearly explained by crystal field splitting, in that we can clearly understand that always the metal atom will be form a bond with the ligand, and the nature of this bond are usually ionic in nature. So what does the crystal field splitting says that, or crystal field theory says that the metal can easily form a bond with the ligand, and nature of such bonds are known as what? Ionic in nature. Okay. Next, ligands are treated as point charges in case of anions and dipoles in case of neutral molecule. Suppose if the ligands is anionic in nature, we consider this is as point charges. If it is like if it is a neutral, we call it as a dipole. So according to the crystal field theory, what does it say? The metal can easily form a bond with the ligand, and nature of the bond will be ionic in nature. Suppose if our ligand is anionic in nature, we consider as a point charges. Suppose if the ligand is neutral, we consider as a dipole. Okay. And the 5d orbitals in an isolated gaseous metal atoms are degenerated and have a same energy. We know that in d orbitals, there are 5 atomic orbitals will be there. Is it right? So when the ligands are get interacted with this d orbitals, it lifts its energy, okay, lifts its energy, which is known as degenerated d orbital, which has the same energy as that of the original one. So only when the interactions of the ligands which is taking place with the metal ion, due to the negative fields of the ligand, the degeneracy of the d orbitals will be get lifted up and results in a splitting up of d orbitals, and these splittings are known as what? Crystal field splitting. And splitting of 5 degenerated d orbitals into 2 sets, they are known as Tg and T2g splitting, and this will be caused due to the interactions of metal ion towards the ligands. Okay. So I'll write once again with that structure. So when the ligands are interacted with the metal, what will happen? D orbitals will be get lifted up by increasing its energy and got splitted into 2 different types, which is known as T2G and EG sets. So which is divided into 2 sets. One is known as T2G, another one is known as EG. This lifting up of d orbital by increasing energy and then splitting, which is taking place into 2 parts, which is known as what? Crystal field splitting. Which is known as what? Crystal field splitting. And the extent to which the energy of the 2 sets of the orbitals can split, which is also known as what? Crystal field splitting energy. And the 3 orbitals of the d orbitals which get separated into Eg and T2G, and it is named as here. So it will be get split into 2 as well as with a 3. You can see that this is DXY, DYZ and DXZ. DXZ, and this is DX square minus Y square, and this is DZ square. This is how the entire d orbitals will be split into 2 sets, which is known as T2G and which is known as EG. This difference in energy we also call it as delta. This is how when the ligands which is interacted with the central metal atom, the d orbital, the 5 d orbitals which lift its energy and split it into 2 sets. This splitting of energy which is taking place in the 2 sets, which is also known as what? Crystal field splitting energy. So the 3 orbitals of DXY, YZ and DXZ are directed between the axis. They are known as T2G orbital, and DZ square minus Y square and DZ square orbitals are pointed towards the axis. They are also known as EG orbital. The ligands which causes a greater splitting of energy, they are known as stronger field ligands. If the ligands are weaker, then splitting is also get weakened, and it is also known as weak field ligand. So it is very important to know that if the ligands are very stronger in the nature, their splitting will be high. If the ligands are weaker, the splitting which is also get weakened and results in the formation of what? Weak splitting, crystal splitting. And we have 2 patterns of splitting also. One is crystal field splitting in octahedral coordination compounds, and the other one is crystal field splitting in tetrahedral complexes. Okay, we'll see the crystal field splitting in octahedral coordination entities. Here you can see that this is my central metal atom which is surrounded by how many ligands? You can see that there are 6 ligands will be there. Is it right? So there are 6 ligands will be there. They are ligating towards the central metal atom. Thereby it forms a 6 coordination number. Is it right? Yes, our 6 coordination bonds will be formed. Due to the interactions of this ligand towards the central metal atoms, what does it causes? It causes a repulsion. Once the repulsions which is caused between the central metal atom towards the ligand, the d orbitals will be lifted its energy. As a result of this, it splits into 2 parts. Already we have understood that the 2 parts are nothing but a T2G and EG sets. Is it right? Yes. In octahedral complexes, the 6 ligand surrounded in the central metal atom, there will be a repulsions between the electrons in the metal d orbital and the electrons of the ligand. So, the dz square and y square and dz square orbitals are directed along the directions of the ligand and experiences a more repulsion, and hence they have a more energy. Whereas dxy and dz and dzx orbital, they are directed between the axis of attracting ligands, hence they are experiences the lesser repulsion, hence they have a lesser energy. The energy separations between the 2 split sets are denoted by delta O, and the energy of EG orbitals are increased by 3/5, whereas that of T2G are decreased by 2/5 delta O. Okay. So, here this is a crystal field splitting of what? Octahedral complexes. Again I am explaining. Here we have what? Metal, and which is surrounded by 6 ligands. Okay. In what direction they have get surrounds towards the metal? So, it will be in the symmetrical direction. Imagine this is a metal where all the ligands are symmetrically, they are directed towards the central metal atom. What will happen when the ligands are symmetrically attracted towards the central metal atom? What will happen? Repulsions will be caused, as I have explained. As due to the repulsion, the 5d orbitals in the metal ions get lifted up and splits into two parts, which is also known as what? EG sets and T2G sets. Is it right? Yes. You can see that between two sets of energy, there is an average energy which is passed at the center, which is also known as what? Barycenter. How does this have written? Only because remember, when the metal which has been surrounded by 6 ligands in a symmetrical directions, what will happen? The metal will experience more repulsion from the ligand. As a result of this, the 5d orbitals in the metal ions will lift its energy and split into two parts. They are known as EG and T2G sets. Okay. In between these two sets, you can see that we have the energy which is average. Hence, it is also known as barycenter. So, what will happen if the d orbitals which is split into two parts? We know that there are 5 atomic orbitals will be there in the d and it will be split into 2 plus 3. Is it right? Yes. So, here you can see that EG has got higher repulsion or it has higher energy as that of from the T2G. Why, ma'am? Because we know that all these ligands, they are directed in X, Y and in the Z direction. Is it right? Yes. Suppose if I take a ligand, okay, imagine you have a metal ion where my ligands are oriented in DXY, DYZ and DZX. Okay, this is my X and this is my y-axis and this is my z-axis. Suppose my ligands which is oriented in this direction x and y. So it will be like this. Is it right? They are all in the plane. Is it right? If it is yz, again y and x. If it is z, again it will becomes in the z and x axis. The remaining what we call ligands, they are present in between this axis. Okay, the remaining ligands, they are present in between these two axes. Hence, their energy will be less. Why it has a very less energy? Because it feels very less repulsions towards central metal atom. Hence, their energy will be less. That is why I have represents this with the 2 by 5 delta 0. So, delta O, which is nothing but a energy gap in a octahedral complexes. Similarly, you can say that dz square and dx square minus y square. How does it looks? So, this is my x, this is my y and this is my z. So, I said it is z square. So, it will be around like this. Is it right? Yes. I said it is x square minus y square. You can see that it is x square and y square. So, in between these two and some of the ligands which is found in between these, you know, they experience a very less repulsion from the ligands. Hence, it is having less energy. But these two ligands, you know, which is found at dx square minus y square and dz square, they are present in the plane. Is it right? Hence, they are experiencing more repulsions. Hence, their energy will be high. That is why I have written 3 by 5 and minus 2 by 5 times. Okay. This is how, if they ask you to write the crystal field splitting in an octahedral structure, you need to write all the structure and you have to explain in your words. Again, it is very, very important and it is very common 3-mark question. Okay. Hope you all understood with this. Next, we have crystal field splitting in tetrahedral complexes. We all know that if I say it is tetrahedral complexes, there will be a one central metal atom surrounded by 4 ligands. Is it right? Then only we can say it is tetrahedral complexes. So, what will happen? We know that ligands which are directed towards the central metal atom, the central metal atom feel more repulsion towards the ligand. As a result of this, the 5d orbitals of the central metal ions lifted its energy and got split into 2 types, and here it is known as T2G and EG sets. you can see that between these two, we have an average energy which is known as what? Barycenter. Once the D energy has been split into two parts, especially the dxy, yz and zx will feel more energy, hence it has 2/5 of delta T, and whereas the another part, that is EG set, which experience a very less repulsion, hence it has minus 3/5 delta T. Why I have written delta T here? Because it is a energy gap between the tetrahedral complexes. This is how if they ask you to write the octahedral as well as with the tetrahedral complexes, please go through with diagram and write neatly to show the splitting of 5d orbitals in the tetrahedral as well as in the octahedral complexes. Next we have spectrochemical series. What does that spectrochemical series tell us? The arrangement of the ligand in the order of their crystal field splitting strength, they are known as what? Spectrochemical series. So already when we are talking this crystal field splitting, we have understood that if the ligands are too stronger, the crystal splitting also it is very strong. If the ligands are weaker, the crystal splitting also become very weaker. That is why they have given the spectrochemical series to understand the order of their ligands with the crystal field nature. So first we have iodo, bromido, thiocyanado, chlorido, sulfide, fluorido, hydrazine and oxalato and aqua, isothiocyanato and EDTA, which is nothing but a ethane 1,2 to dinitrate, and NH3 is amine and EN and CN minus, and which is nothing but a cyanido, and CO is a carbonyl. Okay, this is how we can understand how this ligands, which is also in the increasing order of their crystal splitting nature. Okay, again this will be asked for 1 mark or for 2 mark. Next we have the electrons in the d orbitals of the metal ion in octahedral coordination compounds. Here just imagine the electrons are there in the d orbitals of the central metal ion. So what will be their nature? Okay, the d1, d2 and d3 coordination entities, the d electrons can occupy what? T2g orbital singly according to the Hund's rule. Is it right? Yes. So according to the Hund's rule, what does it say? If the electrons, if the 1 electron and 2 electrons and 3 electrons are there, so the pairing up of electrons will be taking place according to the Hund's rule. And if d4 ions are there, the two possible patterns of electron distributions will be arises up, and the fourth electron could either enter to the T2g level and pair up with an existing electrons, or it can occupy at EG level. So I can write this. Okay, this is my degenerated d orbitals, which will be splitted up into Tg as well as with the, this is T2g. Suppose if 3 electrons are there, we will fill the electrons according to the Hund's rule. Suppose if 4 electrons are there, we have to push up this electron to the EG level. Is it right? Yes. We will write the EG level, but that depends upon the delta O. What is the delta O stands here? Delta O is nothing but an energy gap in the two sets. Okay. So, as well as with the pairing energy. Suppose if the 4th electrons is there, we have to fill this electron to the EG level. Either we have to write it here. Is it right? So, this is depends upon the difference in energy between these two sets as well as with the pairing energy. What is that pairing energy here? The pairing energy stands like this. The energy which is required for the electron pairing in a single orbital, which is known as what? Pairing energy. What is the pairing energy stands here? Pairing energy means electron can easily pair up with a single orbital, which is said to be pairing energy, and we represent it in a capital P. Suppose you imagine the two condition where this delta O, which is lesser than pairing energy, what will happen? The fourth electrons will be enters to the one of the Eg orbital and giving rise to T2, 3 and Eg1. Is it right? If 4 electrons are there, only when delta 0 is greater than P, what will happen? So what will happen? The fourth electrons we have to write it in a Eg level. So their crystal splitting will be become T2G3 and Eg1. This is in our first condition. Suppose if delta O is greater than pairing energy, what will happen? This electrons, so we have to pair up this electron in the T2G level and give rise to the T2G4 and Eg0. Why it is Eg0? Because here we have considered the condition of delta 0 which is greater than P. Okay, in such situations we have to fill the fourth electron has to be paired with a single orbital. So this is how, if the 4 electrons are there in the d orbitals of the octahedral complexes, their shifting of electron towards the Eg and T2G sets, which also differs by depending upon the two assumption, either it will be in the delta O which is lesser than P, either delta O is greater than P and giving rise to this different complexes. Suppose if you got these complexes as I have explained with the T2G3 Eg1, usually such ligands are weaker and it forms a high spin complexes. Suppose if the electronic configuration, if you got like T2G4 and Eg0, the ligands will experience a strong repulsions, hence it is a strong field ligands and forms a low spin complexes. This is how the electrons in the d orbitals of the metal ions, especially in the octahedral complexes, can be explained based upon their splitting. Okay. So in the next class, again we are going to discuss with the last topic, that is colors in the coordination compound. By this, I like to say that which are all the things which I covered in this session, especially for the crystal field splitting. So many times it has been asked for the 3 marks. Okay. So always look into the octahedral as well as with the tetrahedral complexes. Practice well with the diagram and try to write it neatly and show the difference in the two sets. Okay. We'll meet with the next session. Till that, take care. Be safe. Thank you.